So welcome to Math 150 multivariable calculus. I will re-put in the notes the link to Green's theorem in a day. If people have questions about that, happy to talk about that. But basically just wanted to use today as an opportunity for people to ask questions on any of the material we have done up until now. If there's anything you have questions about, happy to go over. If you want to see certain types of problems, just let me know, happy to do them. So are there any problems people would like to see? Okay, so fortunately I should be able to scroll back and see what that one was. Okay, so it's like this one, calculate this integral. Okay, so a problem similar to this. Okay, so when you have problems like this, you have three pieces of information. So we have, an integral over some region R, f of say xy dx dy. And we have 1 is the region, 2 is the function, and then 3 is the Jacobian. So what we need to do in a situation like this is we have to figure out, what does the new region look like? What does the function look like when we change? And what is the weighing that we have to do from the dx dy to the new thing? So when you look at 9x squared plus 4y squared, is this going to be something that's very nice? D is the interior of the ellipse. This problem, we have shoot. Okay, so for this one, we have the region x over 2 squared plus y over 3 squared is less than or equal to 1. So more generally, we could consider x over a squared plus y over b squared. Let's do, z over c squared is less than or equal to 1. So let's say I give you this region. So this would be a 3-dimensional ellipsoid. This would look like a football. We need to figure out what should the new change of variables be. This is much, much easier than polar or spherical. And the reason is in polar and spherical, you have the change of variables. X is going to depend on both r and theta. Y is going to depend on r and theta. Or conversely, r is going to depend on x and y. Theta is going to depend on x and y. Over here, I have 3 variables, x, y, and z. I need 3 new variables. What should I call them? Yeah, UVW. If I had 4 variables, I'd have to go UVWX. Oh no, that's not good. But UVW works very well. So I want to go from X, Y, Z to UVW. And in a general change of variable, X is going to depend on all of UVW, or U is going to depend on all of X, Y, or Z. For this one, it's actually particularly nice. Any thoughts on what we should set U to be? What would be a good change? Yes. Yeah, X over A. So U should just be X over A. V should be Y over B, and Z, oops, sorry. And W should be Z over C. Or equivalently, X is AU, Y is BV, Z is equal to, okay, it's unfortunate, according to our policy, there's going to be a quiz tomorrow. So this is the one day when it's actually completely fine to have that happen. So X, Y, Z would just be AU, BV, CW. The next thing we need, that's one of the pieces we need. The next is we need to figure out what does dx, dy, dz go to? Well, we can see that's just going to be a, b, c, du, dv, dw. And just, if x is equal to au, then dx is going to be a times du. So the change in the volume element is going to be really nice. We're just doing a simple rescaling. What does the region look like? Well, originally it looks like an ellipsoid. What does it look like now when I go into UVW space? What equation do I get? I'm going to get a sphere. In fact, I'll get a unit sphere, and it'll just be u squared plus v squared plus w squared equals 1. So if I want to have an integral over the region x over a squared plus y over b squared plus z over c squared of, say, e to the let's do negative x over a squared plus, I'll put this in brackets, y over b squared plus z over c squared. Yes?
Why did you add a third dimension of c?
Because I was not asked to do the original problem. I was asked to do a problem like that. And since the problem is in the solution key, which I'll be posting, within an hour or two, I don't want to do exactly the same problem in the solution key because you can already get that. So I want to do something similar. So I'm going to do this one. And I will do this to the 3/2 power dx, dy, dz. So I want to do this integral. So I have, three things. I know this part over here becomes the unit sphere. I know this is going to become a, b, c, du, dv, dw. And now I have to figure out, what does this become? So what would this become? Anybody have a guess as to what e to the negative x over a squared plus y over b squared plus z over c squared to the 3/2 would become? Yes. Exactly. Yep. It's exactly what it would be. Is I replace f of x, y, z with f of, so f of x, y, z replaced with f of x of UVW, y of UVW, z of UVW. Okay. So we just get that this is just going to be the integral over u squared plus v squared plus w squared. This was less equal to 1, less equal to 1, e to the negative u squared plus v squared plus w squared to the 3/2 a, b, c, du, dv, dw. Any thoughts on how we would then deal with this integral? What should we do now? So how should we handle this? Yes. Does it matter if I use x, y, z as my Cartesian coordinates or UVW? I can use whatever I want. This is just integrating over a sphere. when you are integrating over a sphere, your default should be spherical coordinates. So this would become ABC. What is the exponential going to be? As I change UVW to spherical coordinates, what would this become? So what would it be? Sure. As I change UVW to spherical coordinates, what would e to the negative u squared plus v squared plus w squared to the 3/2, what would that become? Y rho squared. I have e to the negative u squared plus v squared plus w squared to the 3/2. So this is the same as e to the what? It would be e to the negative rho cubed. U squared plus v squared plus w squared is just rho squared. It's how far am I the square of my distance from the origin. So I have rho squared to the 3/2. So this is just going to be e to the negative rho cubed. What's my volume element of the spherical? Rho squared sine of phi d rho d phi d theta. So I've got to figure out the ranges. What does rho go from? I said rho. Nope. 0 to 1. 0 to 1, right? Rho is just my radius. I'm doing a unit circle. What does phi go from? 0 to pi. And theta goes from 0 to 2 pi. So which is the easiest integral to do? The theta. In fact, this splits as 3 different integrals. This is just going to be a, b, c. Integral theta goes from 0 to 2 pi of d theta. Integral phi goes from 0 to pi of sine of phi d phi. And then integral rho goes from 0 to 1, e to the negative rho cubed, rho squared d rho. So what do I get when I do the theta integral? So integrating d theta from 0 to 2 pi. I just get 2 pi. Now I have to integrate sine of phi. What function has derivative sine of phi? Negative cosine. And when you evaluate it at pi and then subtract at 0, you're going to just get 2. So I'll leave you to do that integral. Now we have an e to the negative rho cubed rho squared. Is this a nice integral? What do you think? So why is this a nice integral? We can do u substitution. Can I use the letter u for my u substitution? Why not? Yeah, I've already used u earlier. U is x over a. So what I really want is I'll put in a factor of 1/3, and I'll have the integral rho goes from 0 to 1, e to the negative rho cubed times 3 rho squared d rho. I'm trying to set things up to be nice. Just making sure I have enough blank pages. Okay. So we now have the integral from 0 to 1 of e to the negative rho cubed 3 rho squared d rho. I need a letter to use. T is probably a good letter. We'll let t equal rho cubed. So dt is 3 rho squared d rho. If I hadn't put in the 3, I would have to have a factor of 1/3 coming in now. As rho goes from 0 to 1, t is going to go from 0 to 1. So this is just going to be the integral t goes from 0 to 1, e to the negative t times dt. So it's negative e to the minus t at 0 and 1. So did I make a mistake?
Can you just go back to that?
I was just putting this in because I know what's coming. I'm about to do it as a change of variable. I have an e to the negative rho cubed. I want to do a u substitution. I just can't use the letter u because I've already used the letter u in this problem. Yeah. If you look earlier in the problem, we set u to be x over a. Once I've used the letter u for one thing, I should not use it again. So I'm going to use the letter t for my substitution. Yeah. This problem was chosen very carefully. You know, I chose it to be u squared plus v squared plus w squared to the 3/2 because I know that would set this up to be a really nice row integral. I could just try to solve this directly by saying what function has derivative e to the negative rho cubed rho squared. It would just be the function 1/3 e to the, or negative 1/3 e to the negative rho cubed. Yeah, this is now a Calc 2 problem. I'm just putting in the 3 just to make things a little bit easier. We don't have to put in the 3. You know, if I don't put in the 3 and I just leave it like this, then when we get over here, I don't have the 3. And so then I would get rho squared d rho is dt. No, I'm sorry, but I would still have the 3 over here. And so now I would get rho squared d rho is 1/3 dt. And so now when I substitute, I have a 1/3 there. It's just a question of, you know, if you know what's coming, you can try to make things a little bit easier. Yeah, I know I'm going to want to do a substitution like this. I know I'm going to have a 3 coming down. Let me just put that in. If I don't see it, I then just get a 3 rho squared d rho. I want a rho squared d rho. I'm off by a factor of 3. So I get that rho squared d rho is 1/3 dt. And so now this changes ever so slightly. I have a negative 1/3 e to the negative t at 1 and 0. So I would get 1/3 of 1 minus 1 over e, I believe. Because when t equals 1, I get negative 1/3 1 over e. When t equals 0, I get 1/3. This is a positive number, which is great because I have a positive integral. So the final answer is going to be, I think it's 4 pi ab c. Yes. So it's going to be 4/3 pi a b c 1 minus 1 over e. And so that would be the answer. So this is the way you would handle problems like this. Start off, have some integral of a region. You know, here I'm writing it in 2 dimensions. The problem I gave you was in 3 dimensions. We have 3 pieces. We have the R, the region. So we have to figure out what does the region look like after we do the transformation. We have the function f, and it's initially defined for x and y, and then x and y are going to depend on our new variables, and we have to figure out what that's going to look like. And then finally, we have the area element or the volume element, and we need to figure out how does that transform. And that's where we calculate the Jacobian. In some problems, we have to actually do the explicit calculations, dx du, dy du, dx dv, dy dv, take the determinant, take the absolute value, so it's non-negative. In a problem like this, it's so straightforward. X is AU, Y is BV, Z is CW, that dx dy dz is just going to be A du times B dv times C dw. And so when we do all this, we end up getting an integral e to the negative u squared plus v squared plus w squared to the 3/2 abc du dv dw. And then the key was to notice that the best way to do this is not to do the integral directly in UVW, but to convert to spherical coordinates. You could, of course, just done this in one step. You could have directly converted to a modified spherical coordinates from the initial problem. I think it's much easier to first convert to integrating on a unit sphere with UVW, and then once I have this, then convert to spherical coordinates, rather than coming up with a modified spherical coordinates from the beginning and just doing it as a 2-step process. For a lot of things in life, it's a lot easier to do a lot of small problems than to just do one big problem, trying to do everything at once and running the risk of making a mistake. But this is how you would handle a problem like that.
I'm just taking.
Yep, just taking questions.
Can we go over the second part of the last question? Since it's given, then we'll do on the lines.
Uh-huh.
So, do you want me to do that?
No, because I'll just give a general problem related to that. So let's say I have two curves. So here's one curve, y equals f of x, and here is another curve, y equals g of x, and I want to find out what 2 points are the closest. So I've got some point here that I'm allowed to vary. I have some point here that I'm allowed to vary. And I want to move the green point on the blue line. I want to move the yellow point on the red line to minimize the distance. And what I can do is you give me any 2 points and I can calculate the distance between them. And one of the things in math is you hate having to deal with square roots. So rather than trying to minimize distance, you often minimize distance squared. So let's imagine that this is at the point RS, and this is at the point TU. Then the distance is going to just be the distance from RS minus TU. And let's square it to look at the distance squared. So that's going to just be R minus T squared plus S minus U squared. So this is a function of 4 variables, R, T, S, and U. But we have several constraints. We have that R and S has to lie on the blue curve, y equals f of x. We have that S and U, that TU has to lie on the red curve, y equals g of x. So one way there's a lot of ways we could do this. I could fix a point on the blue curve, and then I could find which point on the red curve is closest to that. So for a fixed point on the blue curve, what point is closest, and calculate that distance squared. That's just a constrained minimization problem. How would I do that? So if I fix a point on the blue curve, how would I find the point on the red curve that's closest? So how could I do this? What techniques do we know that would work? So method 1, fix a point on the curve y equals f of x, find the point on y equals g of x that is closest by using what? What method? Lagrange multipliers. And so I should then be able to have a constrained optimization problem. The point TU has to satisfy U equals G of T. So I have, I fix RS on the line on the curve y equals f of x. Find TU closest with U equals G of T. So distance squared is going to be R minus T squared plus s minus u squared. And the constraint is going to be u minus g of t equals 0. So what are my variables? What are my free variables right now? T and u.
Question. How did you set up that constraint?
T has to be on the red curve, right?
So you said u minus g of t.
So u equals g of t.
Yeah.
Did I write it the wrong way? Yeah, no, u equals g of t or u minus g of t equals 0. So I just have to be there. My free variables are t and u. So I would get, if I call this distance function, let's call it, L of t and u, I would get the gradient of L is lambda gradient of, I need a constraint function. I'll call this, C of ut. And I would get u minus g of t equals 0. So this would be 3 equations, 3 unknowns. So I could get, dl du equals lambda dc du, dl dt equals lambda dc dt. And then my last equation is going to be u minus g of t equals 0. 3 equations, 3 unknowns. And then I get the optimal uv as a function of the fixed R and S. Okay. So now, if you give me a point RS on the blue curve, I can tell you what point on the red curve is closest. I can tell you what the smallest distance is. Now, what should I do? I wanted to find which 2 points were closest. I said, if I choose a specific point on the blue curve, I can find which point on the red curve is closest, and I can find what that distance is. Now, what do I do? So I'm trying to find the closest the 2 curves come to each other. That's a hard problem because I've got the green point moving on the blue curve. I've got the yellow point moving on the red curve. So rather than doing this hard problem, let me break it into 2 easier problems. I'm going to first fix a point on the blue curve. And now that I've fixed the point on the blue curve, that point's no longer moving. For now, that green point is fixed. And I just moved the yellow point along the constraint y equals g of x. So t equals g of u, because it's got to be on that curve. And for that fixed value of RS on the blue curve, I can find which point on the red curve is closest, and I can find what that distance is. But that doesn't answer the problem. The problem was, which 2 points are closest or what's the smallest distance between them. I was able to find for a fixed point on the blue curve, what's the shortest distance. Now what do I do? Nope, that's not how you would want to go here. I fixed a point on the blue curve, and I found for that fixed point, what's the closest. So how would you then find? So for each point on the blue curve, I can associate a number. How far are you off from the red curve? What's your closest distance to the red curve? For each point on the blue, I can associate a number. The smallest distance to the red curve. I want to find the smallest distance overall. For each point on the blue curve, I know the smallest distance to the red curve. What should I do? I'm sorry? What do you mean by use another set of points?
really simply run it through this. So I just would use the red dot. So
Well, I'm saying you give me any point on the blue curve, and I can find the point on the red curve that's closest. And I'll attach that number. Let's say it was 2 units here. I can choose another point on the blue curve and find which point is closest. Maybe it was 3. I can choose another point on the blue curve and find the distance. Maybe it was a half. For each point on the blue curve, I can associate the number closest distance to the red curve. I want to find the smallest of all these numbers. What do I do? Okay, but so what do I do? So I would just do Lagrange multipliers again. I can view this as 2 Lagrange multipliers. You know, what I can do now is for each point on the blue curve, you know, y equals f of x, I can associate, you know, a number. I will call it, you know, capital A of, what am I calling it? Am I calling it RS? I think it's RS is what I'm using. So you give me a point and I can associate some number A of RS. This is going to be the shortest distance to the red curve. So now I want to minimize A of RS subject to S equals f of R. It's another Lagrange multiplier. I can do this as 2 Lagrange multipliers. First, I fix a point on the blue curve, and I use the Lagrange multipliers to find the closest distance. And now that I have that, now I vary things on the blue curve. So now I would have the gradient of A is equal to lambda gradient of, let's let, you know, C of RS be my constraint, which will be S minus f of R equals 0. So I'll use capital C. And then subject to S minus f of R equals 0. So again, I will now have 3 equations and 3 unknowns. You know, dA dr equals lambda dc dr. dA ds equals lambda dc ds. And S minus f of R equals 0. So one way to do this is to do it as 2 Lagrange multipliers, one after the other. So that's one way to approach a problem like this. Another way is, you know, we have, so method 2, we have RS on the blue, y equals f of x. We have TU on the red, y equals g of x. The distance is r minus t, or distance squared, plus s minus u squared. But we know our constraints, so we can just feed the constraints in. Or the distance as a function of r and t is just going to be r minus t squared plus s is going to just be f of r, u is going to be g of t. So that's my distance function. I've just incorporated the constraints directly into my distance. I want to minimize this. I want to find the r and the t that give me the minimum value. And again, because these are curves of the form y equals f of x, y equals g of x, once I give you the x coordinate, you know the y coordinate. Yes. Well, I know the point RS is on the blue curve y equals f of x. So if I give you the x coordinate as r, what does the y coordinate have to be? It has to be f of r. So S has to be f of r. And since tu is on the red curve, and that's the curve y equals g of x, I have to have u equals g of t.
And that's what you told me.
It's another way of looking at the calculation. I can do it as two different Lagrange multiplier problems. I can say, let me first fix a point on the blue and find the point on the red that's closest and see what the distance is. And then once I've solved that, then let me vary the point on the blue. Again, it's taking a hard problem and rather than doing one hard problem, doing two smaller problems. It's really hard to figure out which 2 points are the closest because I have two different points that I'm varying. Well, what if I give you the easier problem of you can fix a point on the blue and then just find the point on the red that's closer? That looks more in line to what you've seen before. So let me solve that problem. But I can solve that for every point on the blue. So for each point on the blue, I can associate some number, let's call it a of rs, which tells me my distance to the red curve. The other thing I could do is I could try to just do one function directly. Well, my distance is r minus t squared plus s minus u squared. Okay, so that's my distance squared. But r, t, s, and u, they're not all independent. Once I tell you what r equals, you know what s equals. Once I tell you what t equals, you know what u equals. This is just using the constraints. If you think back to the Farmer Brown problem, when we had a farmer who loved rectangular pens and would not consider any other type of pen for the cows, we could do this as a multivariable calculus problem. I want to maximize the product xy subject to x plus, or maybe 2x plus 2y equals the perimeter. That's one way to do the problem. The other way to do the Farmer Brown problem is to say, well, if 2x plus 2y equals p, then y is equal to p minus 2x over 2. And I can substitute that in and make it a function of just one variable. So I can either use Lagrange multipliers with a constraint, or I can take the constraint and use it to directly remove one of the variables. So if I do this now, I now have this function to minimize, and it's a function of r and t. So how would I find where this function is smallest? What would I do? So I'm giving you a function of two variables. How do you find where it's smallest? So if I give you a function of one variable, how do you find where a function of one variable is smallest? You find critical points. Anything else we need to worry about? Endpoints, right? So for one variable, we have to worry about endpoints. For two variables, we have to worry about a boundary region. Well, fortunately for this, r and t are going off to infinity. There are no endpoints for this. So I just look for critical points. So find critical points. So I want the gradient of the distance function. Is it equal to 0 the number or 0 the vector? 0 the vector. So that's going to be equal to d distance dr, d distance dt, and that should be 0, 0. And now I just have to solve that. And so depending on what f and g are, this is going to be potentially either easy or hard. So now I want to take the derivative with respect to r. So the derivative with respect to r would be 2r minus t plus 2 fr minus g of r times f prime of t. So it would be 2r minus t plus 2 f of r minus g of t times f prime of r. And then I would have to take the derivative with respect to t. Depending on what f and g equal, this could be a very painful problem to solve. So if I'm giving this to you on an exam, you would only be asked to find an exact closed form solution if the numbers are nice. And it ended up being a cubic where with divine inspiration, you could see one of the roots. Once you know one of the roots of a cubic, how can you find the other roots? I'll try not to smile too much. What hated technique from high school from algebra 2 can you use? I've got a cubic and I know one root. That's hard not to smile. What painful technique? I'm sorry. Quadratic works only if you have a quadratic equation. I'm giving you a cubic. I'm not going to expect you to use the cubic formula, but imagine you know one root of a polynomial. What can you do to then find the next roots? This is polynomial long division, right? If you know one of the roots, if you know 5 is a root, then your polynomial is divisible by x minus 5. Divide by x minus 5. If you have a cubic, what will you get if you divide by x minus 5? What kind of polynomial will you get if you divide a cubic by x minus 5? It is extremely painful for me to be speaking right now with the missing tooth, so please help me. You have a polynomial of degree 3. We know x minus 5 is yes. You would get a quadratic. What can you do now that you have a quadratic? Now you can use the quadratic formula. So if I give you a cubic where you happen to be able to guess one root, does anybody remember how you can find certain roots of polynomials? Anybody remember the techniques? The rational root test. So if your polynomial has rational roots, you're of the form P and Q, then there are rules about one of them divides the constant term, one of them divides the leading term. There's only finitely many candidates. So if you actually have a cubic and one of the roots is rational, there's a very small finite list of things to try. And so any problem I give you, if you are asked to find something like that, would have to be something which is very nice and straightforward. But on the exam, I think that was actually worth 0 points to the exam. It was entirely extra credit. If you've completed everything else, can you find what the roots would be? And it was designed to be a nice cubic. So this is a good problem in that there are two very different ways of looking at it. I can look at it as a string of Lagrange multipliers, where I'm optimizing one thing after the other, or I could just substitute everything in and just reduce it to a new problem. There's no constraints now because I've used the constraints to remove two variables. I start off with, I want to minimize the distance squared. If I didn't have any constraints on where R, S, and T you had to live, what do you think you could make the minimum distance to be? 0, right? How would you make the distance 0? Yeah, just choose them to be the same point. So clearly, if I have no constraint on the 2 points, I can make the distance as small as I want. So then it becomes interesting if I tell you I have to be on 2 different curves. And you might want to know what's the closest you can get. This can become extremely important for some orbital mechanics problems. Okay, we have time for maybe 1 or 2 more questions. Anything else? So in general, if I give you an optimization problem and I say, I want to say, find the largest or the smallest value on or inside a sphere or on or inside an ellipsoid, it's 2 problems. It's finding the critical points inside the region, and that's just finding where the gradient is 0. And then it's finding the constraint points on the boundary. And for the boundary, that's where you have to say, I want the gradient of f to be in the same direction as the normal, the gradient of g. The reason it's a lot easier in the interior is in the interior, you can move in any direction you want. And so if you can move in any direction you want, if the gradient is not 0, it can't be a maximum or minimum. Whatever direction the gradient is pointing, if you go in that direction, your function's increasing by the definition of the directional derivative. If you go in the negative of that, your function is decreasing. So if the gradient is not 0, your function can't have a maximum or minimum. If the gradient is 0, do you have to have a maximum or minimum? So does every function where the gradient is 0, do they always have a maximum or minimum? You think back to one dimension. If the first derivative is 0, do you have to have a maximum or minimum there? And if not, you should be able to give me a function which has 0 derivative, but is not a maximum or minimum. Yeah, x cubed. X cubed is a really good go-to example. So when you look at x cubed, it does not have a maximum or minimum at 0, but the first derivative is 0. What goes wrong is that the second derivative is also 0 as well. And so these are only giving you candidates. You think of it as a necessary versus a sufficient condition. It's necessary for the gradient to be 0. It is not sufficient for the gradient to be 0. When we do sequences in series, if I ask you if the sum converges, what's the first test you should do? Yeah, does the nth term go to 0? If the answer is no, you're done. It can't converge. But if the nth term goes to 0, then it may converge. It means you have to do more work. And then you can go through all the different tests we know. We know the ratio test, we know the root test. Unfortunately, if you do either ratio or root, you might either have a limit that's hard to compute, or you might get one which gives you no information, in which case you have to do more analysis. We have a p series, the sum of 1 over n to the p. It converges if p is greater than 1. It diverges if p is less than or equal to 1. Easiest way to see this is to use the integral test. But if you take the ratio or the root test for 1 over n to the p, you get 1, no information.
On the note of like series tests.
Yes. Well, let me see if anybody else has a question first. Okay, everyone else's question has been answered. Okay. I'm sorry? Okay.
So this is question 3,
This
is so the series is as n goes to 1, and then 150 to the power of n x times x to the power of n all over n.
Oh, 150 to the n times what?
Times x to the power of n all over n.
Okay. So there's a couple of ways to do this. The easiest way to do this is, remember e, I'll use a different letter. E to the u is 1 plus u squared over 2 factorial plus u cubed over 3 factorial plus dot, dot, dot. What should I take u to equal? So what's another way to write the numerator of this? How else could I write 150 to the n times x to the n? What's another way of writing that? Yeah, 150 x to the power of n. Any thoughts on what would be a good choice of u? Yeah, 150x. So it converges to e to the 150x. So one way to solve this problem is to just note that I'm just taking the series expansion for e to the u, which converges for all inputs, and just putting in u equals 150x. You could try to do the ratio test. If I do the ratio test, I'm going to get rho is the limit as n goes to infinity, an plus 1 over an. So the limit as n goes to infinity of an plus 1, so it's going to be 150n plus 1, x to the n plus 1 divided by n plus 1 factorial over 150 to the n, x to the n over n factorial. So that's the limit as n goes to infinity. 150 n plus 1 over 150 to the n is 150. X to the n plus 1 over x to the n is x. I multiply by n factorial over n factorial. And when you do a little bit of algebra, you just get n plus 1. I can pull the 150x outside of the limit. And I just get the limit as n goes to infinity of 1 over 1 over n plus 1. What does that limit equal? 0. So as rho equals 0, which is less than 1, converges for all x. And so you could do this with the ratio test. You could also do this with the ratio test, but a little bit more work. All right, so I'm going to stop it here.